All right. Michael's here. Chad is here. Bridget. And Reagan. Lindsay. Dick Shaw. Austin. Zach, Sally, Cassie, Kayla. Jerry. Jared. Okay, I see everyone here but Anne, who it's probably reasonable. She probably is home because the roads are much more treacherous today than yesterday. We always make these decisions in an odd fashion. It's kind of comical to see our decision making on snow closures. You know, there are times when it's like everybody's slip sliding everywhere. Come on, we're a community campus. We can all make it. And other times, like yesterday, you know, they canceled classes at 5 p.m. on Monday. We already knew at that point the storm was mostly going to miss us. But, you know, and of course, yes, the storm did miss us for the most part. How many inches did we get? Several.
Someone has 8 somewhere.
I don't think in Lincoln.
Yeah. I mean, in our backyard there's 8.
Really? I mean, we had like somewhere around 4 to 5. I probably lost our household bet with my bet of 3, but it wasn't too far off. Anyway, so we didn't have school yesterday, which meant that we did not have lab yesterday. And I was counting on lab for you getting your practice with Kirchoff's laws. So I'm going to lecture primarily on Kirchoff's laws. I also did a little tutorial video last night. It's a little bit humorous because some people asked to do a simplification, solving a circuit through simplification first. I did that. And in the final step, I inserted a 1. It's like supposed to be 3.57 or 4.57. I put, 0.157, which made my answer wrong. And I was like, well, it's not going to be worth my time to go back and try to find where I made the mistake. It was at the very last step. So if you watch that and you get there, you'll probably notice, wait, he wrote down the wrong number. Oh, she made it in. Did you slide and crash? I'm assuming the answer is no, you didn't crash, right? Otherwise, I wouldn't ask that question if I thought you possibly had. But was it Harry driving in? Little. I was like the world's most unsafe driver this morning. But moving on. So what we're going to do, I do have that tutorial where I work through solving a different problem using what we call loop analysis. Now, those people who take a circuit class have learned mesh analysis, which is a slightly different variation of loop analysis. And I'm going to go through today and lecture on that as well, so you can watch the tutorial for another explanation on it, given instead of a lecture sitting in my bedroom. And we will, at least right now, my plan is to skip the Kirchoff's laws activity completely for lab. That includes the reading or the pre-lab quiz, so that, if you miss one, it won't count against you on that. If you didn't do it, it won't count against you, because clearly we didn't have lab yesterday. Still do the rest of Chapter 22 concept coach questions for class on Friday, and we're still on schedule for having the exam next Tuesday in lab. Yes?
So about that one, according to the schedule, the concept coach goes through 22.12, which we have for next Monday. Just stick with this.
Does this? I thought that it said that we finished 22 on Friday. Yes, stick with that. Yes, okay. Stick with that.
It says 22.5 to 22.8 for Friday.
And of course, if it says 0.8, that really means 0.7 because they took off all of the 0.1s. And everything got dropped 1. Okay, moving forward then. So thank you for correcting on that. I looked at the schedule and thought that I finished Chapter 22 next class period. So we're going to start with a repeat question. Which terminal has a higher positive voltage in the figure below? Answer, Sally. Answer. There we go. Now she answered. Okay, 117.00. Okay, The 17 are correct. That's good. It's a good sign that we mostly have this. Remember, energy is required to force charge to go through, and so the side the charge enters is the positive, the side it exits is the negative. What's actually going on is electrons are going the opposite direction, but we talk about it with the mythical positive charge going through the wire.
Question.
Yes?
On Monday, you had a slide, I think before this one, that showed a couple different scenarios, and you had one where the arrow was reversed and you called it a negative current, I think, or something of that nature.
I would have to look back at what you're talking about. I do remember having the slide where I had this, and then I had a power supply that goes like this, and the current goes like that. So the current has the plus on the opposite end of the arrow for the power supply because it's supplying power. That's not what you're thinking about? Yeah, so I would have to look specifically to be able to answer that. I'm not sure. Okay, so jumping right into it. I looked at the wrong thing. Find the current through and voltage across each resistor. When you solve a circuit problem, now what we're learning, like I said, this is kind of the beginning technique. The mesh currents is a little bit easier but a little more complicated conceptually. So this is the simplest conceptually. The first thing you need to do, step one, is label currents in the circuit. So this circuit has current 1 shown here through resistor 1. Current 2 right here and current 3 here. What would you tell me about the current going through resistor 2? Resistor 2 is right here. Right there. What are you telling me about the current going through that? No, that's the resistance. Anyone? Bueller? Yes, it's just current 2 because this current, all of these things that are in series have to have the same current. We call these items in series a branch. So a branch is a collection of things that are in series. Could be just one thing in the simplest case. And everything in the branch has the same current. So I've got to change back to the pin. So I have I2 through this one and I2 through that one. Likewise, following I1 goes like this and like that. And then I3 is here, so that means I'm going to have I3 there and my writing is getting sloppy. Well, I3 there. So I've labeled the currents through every resistor. Step 2 is mark plus and minus for each element. Now, do you have to do this? You don't have to, but it's going to make life easier as we go through the problem. So I take this using the question we had in the preceding clicker question. It's going to be plus to minus. This one here, plus to minus. The power supply, those come pretty automatically. So I've marked the positive side and the negative side for each element in my circuit. I've done that so I will make less mistakes, less chance of making a mistake, in the further pieces. Next step. Identify each mesh. Now on the tutorial I made, I talked in a fair amount of depth about what the meshes are and why we use them. The meshes are just the smallest loops you can make. So how many smallest loops can I make? 2. And so I'm going to identify them, and identify them with a direction and a label. I always just label them 1 and 2 and always go clockwise. I have my way of doing it so I won't make a mistake. You can go clockwise or counterclockwise, it's up to you. But I just have my way so I don't make mistakes. So I identified each mesh. Meshes are the smallest loops. Finally, step 4. Identify each essential, whoops, that's not how I spell essential, node. So the meshes were the smallest loops. I've talked about essential nodes. What were essential nodes? Places where 3 or more come together. Now, this picture had every single node labeled. So I can just ask you, is A essential or not? A is essential. So I'm just going to put a box around the essential ones so I remember them. B, is B essential? No. Okay, so I see people who've picked up on it. There are 3 things here, only 2 there. That's the difference. Why did I put a box around B? Because I completely forgot. C, D, non-essential, or C is non-essential, D is non-essential, but E is another essential node. F, G, H, I, J, those are all non-essential because they only have one thing attached to each. Question?
You said they have to have 3 or more what attached to them?
3 or more elements. Basically 3 wires come together or less, or more. I mean.
It's the point where they come together.
Yeah. So here I have 2 essential nodes, A and E. I have 2 meshes, 1 and 2. Now we're ready to do our work. So do your work. The order you do these steps isn't super important after you've done the first 4. And so I am just going to do it the way I do it. 5. Use Kirchoff's voltage law on each mesh. So I have 2 meshes. I'll use Kirchoff's voltage law on each one. So let's look at mesh 1. Kirchoff's voltage law. Sum of the, what's Kirchoff's voltage law tell us? Sum of the voltages on a loop is equal to 0. So now, once again, the way I always do this so I don't make a mistake. You can start anywhere you want. You can go any direction you want. I always simply start at the bottom left-hand corner of my mesh so I know where my start and ending points are whenever I do one. It just makes it easier for the bookkeeping. So I'm going to start here at node A, and the first thing I do is I go through resistor 1. Is the voltage going to go up or down when I go through resistor 1? Down. How did you know? Okay, I put the pluses and minuses. I'm going from plus to minus. That means I'm going down. So I'm going to have minus. I don't know what that voltage is, but I know Ohm's law. And so Ohm's law says that voltage is going to be I1 times R1. Now I keep going and I come next to my power supply. Going from minus to plus, so is that a drop or a rise? It's a rise, so that's a plus sign. And I'm going to put here E1 instead of putting in numbers. I don't like to put in numbers until I have to. Now I have that lowercase r1. The lowercase r1, what's the point of that? That's the internal resistance of the battery. If r1 is virtually 0, the battery's in good shape. If the battery is going bad, the chemical reaction is slowing down, that makes r1 a bigger value. So r1 is basically telling us about how quickly the chemical reaction can occur. A value of 0.10 ohms is pretty low, so it's pretty good shape. Going from the plus to the minus, so that's going to be minus I1, lowercase r1. R5, once again going from plus to minus, so minus I1 R5. Now going from E back to A, going through resistor 2, am I going up or down? Now going up, because I'm going against the current arrow. And so that's going to be plus I2 R2 plus I2 lowercase r2. And finally, going through that battery, is it going up or down? Down, minus E2. So there's my equation. Pretty long and drawn out, right? Because this had a bunch of resistors on that loop. Now we go to the second loop. And I'm actually going to change colors for each equation. So the second loop, or the second mesh. And once again, I start down here at node J because it's the bottom left corner. I'm going, and now I want people to tell me what each piece is going to be. So I'm just going to go this side here and go straight back to the back and then come up. So what's the first thing I encounter there?
That'd be negative I3R3.
Negative I3R3. Okay, next Ann. Plus E2. Next, Michaela.
Negative I2 little r2.
Okay, Jaren. Okay, what's the next element? The one that comes after lowercase r2 in the circuit, Jaren. Capital R2. And so is the voltage rise or voltage drop? Okay, so what is my thing that I need to write then?
Minus R2 I2.
Okay. Bridget, what's the next one?
Are we at the R4 one?
Yes, that's
Okay, minus I,
that's a 3, yes.
I3 R4.
Lowercase r4.
Yeah,
Okay, Diksha, what's the next one? We're going from positive to negative. Oh, I didn't mark these here. Positive to negative, so that means we're going down. And then Charday.
minus I3 little r3.
And finally, Cassie.
Minus E3.
We're going from minus to plus, so we're going up, so it's
Okay.
plus.
How do you know if it's minus or plus?
Okay, I'm going around in a loop. So I was going around in this direction. So for each element, so for instance, the one Cassie had right here, I'm going from the negative side to the positive side. And so since I'm going negative to positive, that's up, so a positive value. If I had done Chad's here, that was going from positive to negative. The reason I wrote those plus and minus signs was so I could do this real quickly. That's a drop, a minus sign. And actually, just for continuation, on the one that I think Diksha did, we had here going from the positive side to the negative side of the battery. That was a negative. Okay, so there's my two mesh equations. Now, anyone who's qualified to be in this class knows that there's a loop that I skipped. I skipped a loop because it wasn't a mesh. Which was that? The one going all the way around the outside. If I went all the way around the outside, I could have a third loop equation. But here's the thing. If I go all the way around the outside, going from A to E is the same as I had in my first loop. And going from E to A is the same as I had in the second loop. And then in between, I am just skipping going from A to E and E to A. So if I did that entire outer loop, it would simply give me the equation that's equal to the sum of the first two loops I did. So it wouldn't be any new information. That's why I had you just identify the meshes. It turns out a very simple theory. It can be proven mathematically. The number of independent equations you can make from a circuit is equal to the number of meshes in the circuit. So since this had two meshes, that means I can only make two independent equations using Kirchoff's voltage law. Any additional loops I choose will just be combinations of the other equations. And so when I'm trying to solve a set of equations, it's not going to do me any good if I use a redundant equation, right? Having 5 equals A and 10 equals 2A, the second equation didn't help me any. So that's why we only did those meshes. So the rule here is make sure that you're covering every bit of the circuit and the number of loops you have is equal to the number of meshes. And that goal is most easily accomplished just by making a loop equation for each mesh. Sally, and then Helena.
How come it's E goes through, the resistor 4 has current I3, shouldn't it be I2?
No, I3 is the current that goes through this entire branch. I2 went through this branch. But here I had an essential node. An essential node, your currents change. Helena. That was the exact same question. Excellent. All right, so now reviewing this, I started with we're going to solve the circuit. And I started right in. What does it mean when I solve the circuit? Yes, I solve to find the currents and voltages everywhere. Solve the circuit means I know everything about the circuit. I know the currents everywhere, the voltages everywhere. When you're using the loop analysis here, what variables am I using? What are the things that are unknowns in my equations? Well, the only voltages are the power supplies, which we were given numbers for. So it's just the currents. So how many unknowns do I have? 3. I1, I2, and I3. So how many equations do I need to solve? How many independent equations do I need to solve for 3 unknowns? That's right, Lindsay and everyone else who said it. 3. I need the same number of equations as I have unknowns. So right now I only have 2 linear independent equations that I can make from Kirchoff's voltage law. So I have to go on to a step 6. And step 6 is going to be use Kirchoff's current law at all but one of the essential nodes. Why all but one? The same reason as we talked about with the loops. If I take the last essential node, it's just going to give me an equation that is the sum of the other equations. It won't be new information. It'll be redundant. Or as we say in math, it will not be linearly independent. Why does linear matter? These are linear circuits. I don't have to say the word linear. But when you teach enough math classes, you start saying linear because if they're not linear equations, you have bigger problems. So I am going to take this, and how many essential nodes did I have? 2. So how many node equations can I make? 1. Which node should I use? Okay, I had a clear answer, A. It didn't matter which one you chose, which is what other people said. So since he said A, I'm going with A. So I look at A. Hugely complex equation here. Kirchoff's current law says sum of the currents at the node is equal to 0. Is a current positive if it comes in or goes out? Okay, I had comes in, I had goes out, and the answer is I don't care. I just need to decide and stay with what I decide. So I like to go with coming in as positive and going out as negative. But you can reverse that as long as you are consistent at each node. You could be inconsistent going from node A to node E. As long as at node A you're self-consistent, you're good. So I'm going to take in as positive. So looking at node A, what currents come into node A? 3. Going out as negative, what currents go out of node A? Okay, so my equation is going to be really, really simple. Okay, it's a lowercase a. Sum of the currents at the node equals 0 equals I3 minus I1 minus I2. You can see that was a real problem. But now I have 3 independent equations and 3 unknowns. All of us are perfectly qualified to solve this set of equations. How would you do it, Luke? You can do it, Luke. You have the force. Zach.
Wouldn't you go like do the series as they go
Well, it's just a math problem now.
Okay.
I have 3 equations, and how do I solve for the 3 unknowns?
Plug them in.
I want to.
Do you get,
Nope, never mind. Okay, the brute force way, the way that actually the textbooks expect somebody at your level to do it, is really hard. You have to take 2 equations and eliminate a variable. And then you take that equation and go to the 3rd one, and you eliminate again so that you have just 1 variable. It's not very fun usually. With 2 equations, it's not such a big deal. But with 3, it gets harder. With 5 or 6, Lord help you, you don't want to do it that way. So how do we do it instead? Let me turn to, how many people here have taken circuits class? Okay, 4 people. How do you solve a set of linear independent equations in circuits class?
yeah, we just use the matrix.
Use matrix. Now, this is not a math class. It's linear algebra that you use, but I want people to understand. Now, I explained this all in the tutorial, but I want people to understand what I'm telling you to do and not just say, and through the magic of a calculator, there's my answer. It is that easy. I want you to understand how it works and not just through the magic of the calculator. So we have 3 equations. Now I'm going to rewrite these equations so that I have all the stuff with the variables on the left side and the answers on the right side. So rewriting these equations, just keeping in the same order as I had them before. Equation 1 would be I1 times R1, minus R1 and minus little r1 and minus R5 plus I2 times R2 plus little r2 equals E2. I left some space there for a reason. But that's just rewriting the equation. So I have the stuff with current 1 plus the stuff with current 2 plus the stuff with current 3, that's the gap I left, equals whatever the answer was. And since this was negative, I had to bring it to the other side, the equal side. That's what made it positive. You got to make sure you're clear with your signs. Making a mistake in the sign is the biggest problem people make. Any question about that simplification, or rewriting, not really a simplification of the equation?
Did you take so you just put the E1?
Oh, I forgot the E1. minus E1. Thank you very much, Diksha. There was an E1 here. I just looked at the E2 and forgot about the E1. It's good to be corrected, let me tell you. It's embarrassing, like I told you on that tutorial I made last night. I inserted a digit that didn't belong, but I get to the end and I'm wrong, and I'm like, what? What? I'm the teacher. Well, it's not supposed to happen. So equation 2, doing the same thing. There are no I1s in equation 2, but there are I2s. There's I2 times minus R2 minus R2, and then plus I3 times E4? Is that really E4? Yeah, okay. Just making sure. Okay, so there I've rewritten that equation. Question? Did I forget something? E2 and E4. Oh, yes, it was on the next line. It's going to stay on the next line, which means I'm likely to forget it again. Man, let's stop making mistakes, and by let's, I mean I. So my A equation, I won't make a mistake here, I promise. I1 times minus 1 plus I2 times minus 1 plus I3 times 1 equals 0. So I've rewritten these equations in an organized fashion. And it's always useful to do this just so I can work the problem out easier. At this point, I will put in numbers. And so I have to put R1, R1, R5, 25.1. So rewriting one last time. R2 plus little r2, 40.5. E2 minus E1, 48 minus 24 is 24. $78.25. Okay, I forgot the order here. It's 4 minus 3 minus 2. 4. 36 minus 6 is 30, minus 48 is minus 18. And then the last one, which is the trivial one, because it's already done. Okay, so this last set is the cleanest way of writing my set of equations. I'm going to put those in a box just so we don't lose them. So there's my set of equations. Now the linear algebra part. Linear algebra involves things like vectors, and we can make row vectors and column vectors. And so I can actually create, let's say, the first equation by simply multiplying a row vector by a column vector. So the first equation can be written as, I'm going to drop off the ohm sign. And the voltage sign. The way this works with columns and row vectors is you take the first item in the row vector times the first item in the column vector plus the second item in the row times the second in the column plus the third in the row times the third in the column. So what I've written here in blue is exactly the same meaning as what I wrote up above in blue. But I can put a second vector in here and add to it. So I can put here 0, minus 40.5, and minus 78.25. And that's equal to minus 18. And now I have both of my equations written out. And of course I want all three of my equations. So I add the final one here. Minus 1, 1, minus 1, 1, and 0. And now I have a matrix representation of exactly the same set of three equations, or a linear algebra set of equations. Now, of course, you're still wondering, I said this over and over when I was doing my tutorial, now you're wondering, why did I do this? How is it helping me? Because at this point it just seems like I'm doing something completely different. Well, how it helps me is that I can define and say that this is matrix A. And I will have column vector B, and actually I want to call that I for current. Column vector I, and then I will have column vector, I called it B in my tutorial, I'll call it C here. So my equation can be written as matrix A times I equals C. Right? That's just a shorthand way of writing the equation. And still you're wondering, how does that help? Well, we all know the idea of an inverse. Like the inverse of 5 is 1 over 5. And what is 5 times 1 over 5? 1. The definition of the inverse is when you multiply the two together, you get 1. Well, we have that same concept in linear algebra. We can make an inverse matrix A minus 1, that means inverse. So inverse A, A. But what you do on the left side of the equation, you have to do on the right side. So I have to do that on both sides. And now what I would get is instead of 1, I have what we call the unit matrix, which is 1, 0, 0, 0, 1, 0, 0, 0, 1. All the diagonals are 1, everything else is not 1. Times my currents, I1, I2, I3, is equal to this stuff. How do you find that inverse matrix? That's something that I'm not going into. But it can be shown mathematically as long as you have independent equations, it exists. So what's important is that it exists. And so what we'll use is our calculators to do the calculation for us. The calculations will do this calculation for us with what we call RREF, the row reduction echelon form. So what you do in your calculator, and I have to go to another page and I don't want to lose what I wrote here, so I'm going to copy it. So what you do in your calculator is you take this set of information, these matrices I make, and you just put in your calculation a matrix that has the number of rows here How many rows do I have? 3. And one more column for the answers. And you put in a matrix that has, forgot to put that. You put into your calculator AC. You're not multiplying A by C, but you put into your calculator as one matrix. And then on the calculator, you hit the RREF button, which actually in your TIs is use the RREF function. And out comes that unit matrix. I'm just going to put 1 here to indicate that's a unit matrix times the values of your currents. Now, does somebody have all these numbers written down? Okay, because I'm going to shift over to the calculator and I won't be able to see this when I shift to the calculator. Also, the calculator I've determined will simply not show up on the recording. I did everything that we did here will not show up on the recording, but I made a separate little tutorial for the linear algebra with the linear algebra stuff on it that does record. It's either one or the other. I can't do both because it's changing orientation on the screen, believe it or not. Do you have a question, Diksha? No, just stretch it. Okay. So now I have my currents. What were the numbers for those currents? Minus 0.3449. And current 2?
0.3788.
And current 3?
0.0340.
Okay, so I have my currents. One of them was negative. What does it mean for that current to be negative? If we go back to the picture, in the picture we have, as you see clearly, we have the current going up and then to the right and down, which made perfect sense because that's the way our battery was set up. But now we got a negative value. If we have a negative value, that means the current is going the opposite direction of my arrow. And so the current is actually going from D to C on the top there and going into the positive of the battery and coming out of the negative. Now what does it mean if the current's going into the battery? I'm charging it. The battery is absorbing energy, it's being charged. Now, some batteries, that means it'll explode. Other batteries, no, they're made for that to work. Depends on the chemical reactions and the design. So when I come to the end, I don't say, oh no, I made a mistake. I'm fine with what I did. I now know what the currents are. I know what the direction is. It's just opposite the direction of my arrow. That doesn't cause me any harm. And so now all of my plus and minus signs for the resistors are going to have the actual voltages will be negative, which means they're in the other direction. Not a problem again. So now I can come back and I can say, okay, the voltage across resistor 1 is equal to I1 R1, lowercase resistor 1. So that's going to be minus 0.3, what were the other digits? Times 0.10 ohms. And so, of course, that's equal to minus 0.03448 volts. So I now have the voltage. It's a minus, and that just means that the side that I marked as positive is actually the negative side. So I can go back and I can determine what all of the voltages are because I determined all of the currents. Now, because I have only 2 minutes left in class, let me talk about a more advanced way of doing this. And this is probably the way the 4 gentlemen in the back rows have learned to do this. This is the preferred method, certainly my preferred method. I do mesh analysis always. And in mesh analysis, what's the primary difference in what you do there? If you were to solve this problem in your circuits class, what would you have done differently right at the start?
I noticed that was different was like when you have like resistors in between the two meshes, you know, like it would have been like that little R2, it would have been R2 times like the second mesh and minus the first mesh or something.
Okay, your difference went back one step before that. That is a true statement. But it went back one step before that. When they do the mesh analysis, they make what we call a mesh current. They define a current that goes through this mesh. And then they define a current that goes through this mesh. Then there's only two meshes, so there's only two unknowns, two mesh currents. But in places where two currents go through the resistor, the actual current through that resistor is going to be the one minus the other. And so in the end, they still have to get currents 1, 2, and 3, but they do the calculations with just two currents. And with just the two currents, then you have the situation that Michael described. So it's giving you less variables. You only have to make your loop equations. You don't have to make any node equations with mesh analysis because you have number of equations equals number of variables. Okay, so we didn't cover any magnetism, but now we've covered Kirchoff's laws and how to solve a circuit. On the exam next Tuesday, there will be a circuit that you have to use this kind of analysis on. And of course, for the homework on Friday, there will be a few problems where you have to do this kind of analysis so that you have the practice that normally you would have had yesterday. Question, Charday? You do not need a graphic calculator to do the matrix, you need a calculator that does matrices. It doesn't necessarily have to be graphic. It has to be matrix. You don't have to use the matrix method. It's just a big time saver.